Hello, welcome to this video where we'll talk about my view, Peppe's view, on transformers neural network. Well, transformer neural network is a cool architecture that comes from a paper which is called Attention is All You Need, written in 2017. And maybe this architecture will cause the death of things like recurrent neural networks, long short-term memories, and GRUs. Why is it so? Well, let's have a look at the recurrent neural network example. So the main idea behind recurrent neural networks is that the output is put back as input. So if we have a look at this schema here that I prepared, we have X, that is our vector of our inputs. It gets fed to the hidden state H, and then the output is put back as input to the hidden state itself, and you do this several times. You do this n times. So for example, if we take the time step, the hidden state at time t, this is a function of the input state, the input vector at time t, so ht, and the hidden state at time t minus 1. So to be explicit, we can explode the graph that we had above, and for example, we can consider the hidden state ht, the one that I am pointing at now with the green arrow. So we can say that ht, the hidden state t, depends or receives input from ht, but also from the previous hidden state h t minus 1, and then it produces eventually the output y. Well, there are problems about that. So generally speaking, the input x is parsed n times by the function f. So generally speaking, the output y can be seen as f to the power of n of the input x. This is not 100% correct, but it's to give you an idea. This causes what is called vanishing gradients problem or exploding gradient problem, because let's imagine that f is slightly less than 1. You do it several times, so you are doing a slightly less than 1 number to the power of n. It's going to become 0, and it's going to explode if the number is slightly above 1. So that's generally speaking what is causing exploding and or vanishing gradient problems. A second problem is this long-range memory problem. What does it mean? It means that let's imagine that you have several time steps. So for example, let's say that you have 100 time steps. By the time that you produce the output, basically its x1 is forgotten by the time it arrives at the step number 100. So information gets lost inside this recurrent structure. And then the third problem, maybe the most important problem, because the first two can be tackled with, but the most important problem is the fact that recurrency in fact kills parallelization. So recurrent neural nets and the other stuff that I mentioned before are slow, because you need to wait the computation of, for example, let's say h at t minus 1, if you want to compute h, so the hidden state at time t. So you need to wait, and you have to do it sequentially. You cannot parallelize by definition of recurrency. And so the effect is that LSTMs, recurrent neural networks, all these kind of things are slow because they cannot be parallelized. Solution to this is called transformers. And that's what we are talking about here today. So transformers are based on attention, and the basic idea is that the output y of I, let's call it like this, is based on the relevant parts of the input vector x. So we can focus, for example, on text translation. So I can give you an example. Let's say that you want to translate a certain word, the height word, in the target language. And you may think that the target word number I in the translated language, in the target language, would depend on some of the input words in the original text that you want to translate, but not with the same weights on all the words of the original text. So basically you want to put more relevance, more emphasis to some of the words that are present in the original text that you want to translate. So you want to put attention, you want to put emphasis on some parts of the input vector x to translate a certain output y of I. That's the main idea. So we want to describe what attention is, and that's what I'm about to do now. So the idea is based on database retrieval. So let's imagine that we have a database. Okay, we have a certain number of rows where we have our keys, for example, key 1, value 1, key 2, value 2, and so on and so forth, key n, value n. And let's say that we have a certain query. For example, we can imagine a query in SQL, so select whatever from the table. At the end, we select the value or the values that are matching a certain query that we are asking the database to match. That's the main idea. So we can define our own attention as something that depends on three things: on our query, the query that we decided, the keys of the database, and the values of the database. And this is gonna give us a weighted sum of the values of the database. And the weighted sum that goes over all the values of our database is weighted by something that is called similarity, and this similarity depends on the query and the keys of our database. And at the end we obtain a weighted sum of all the values weighted by these weights A of I. So in the attention mechanism, all values are considered, but they are reweighted by taking into account how similar the corresponding key is to the external query. Let me tell a few things about the similarity here. So what appears as weight in the attention definition. So one example of similarity is this. This would be a rule to compute the similarity. We have our key, we have our query, we compute the dot product between the query and the key number I. Then the similarity is computed as the softmax of q and k of I. So we exponentiate the dot product of q and k of I, and then we have a normalization factor. This is by definition the softmax between the query q and the k con I, and this is a number that belongs that stays between 0 and 1. So this is what I called A of I in the definition of attention. Finally, we have our attention as the weighted sum of all the values weighted by this A con I, and this A of I are weights that basically are computing the alignment between the external query and the keys. That's the idea. So now we have one question. One question could arise at this point. What should I pick as my query, my key, and my value? Let me make an example in machine translation again. So let's imagine that we have this text, the original text that we want to translate. Now I'm going to use my favorite language, German, of course. Ich bin schön und sehr intelligent. This would be the initial test that we want that we want to translate. So I labeled the words belonging to this text as x1, x2, all the way down to xn, and we want to translate this, let's say, in English. So one proposition for query key and value would be to use as query the hidden vector height, the height hidden vector for the height output word. That would be our query. As key, we can use h of I, which would be the hidden vector for the height input word. So the query would use the height output word. The key would use the height input word. And then as value, we use h of j, which would be the hidden vector for the jth input word. With this definition of query key and value, we can compute our attention. That depends on I, because we have several queries that are indexed by the output words, and we have a certain number of output words in the target language. Let's say that we want to translate this German text into English. So we have a certain number of words in English, our target language. So the attention depends on I simply because we have n different queries indexed by the output words. This would be a weighted sum of the values, and we decided that the values are the hidden vector of the input words, and those are weighted. So this sum, if we use sort of the Einstein notation, this sum goes over j, okay? So we have m input words in German, we sum over all the values, and then the similarity depends on the I, which is our fixed target word, output word that we want to translate. And so if we specify the formula, so if we want to be explicit, we sum over j, so we are summing over the input words in the input original text. So in our German text, we are computing the similarity between s con I and h con j. We are summing over j, and this would give us the attention that is based on all the values. So all the input words are weighted in our final attention. And this again makes sense because if we want to translate again the height word in English, let's say that our target language is English, we want to pay attention on all the words of the original German text, but with different emphasis depending on the word that we want to translate. And that's a bit the idea of this attention mechanism. So all in all, not all input words are equally important to translate the ith output word. You should pay attention only on the similar ones, so on the ones that are more similar to the word that you are interested to translate. That's the idea of this similarity S con I, H con J. That's a bit it. So you can think about it sort of in a natural way, because if you want to translate something as a human being, you do not pay attention on all the text. If you want to translate one particular word, you are focusing only on some of the words of the input text. That's a bit what this similarity or attention mechanism is doing. So we are kind of imitating what a human being would actually do. So let's summarize a bit our attention mechanism. So we start from some keys. We have K1, K2, Key 3. We have our external query. We can have even more than one query, as I just mentioned before. Given a key and our external query, we compute our similarities. Similarity 1, similarity 2, similarity 3, and so on and so forth. Given the similarity, we can compute the weights A of I as the softmax of the similarities that we just computed. Finally, the attention is the weighted sum of all the values weighted by this A of I that we just computed. We just gave the definition of what A of I are. Or if you have M queries, the example that I did before, we have M target words in the translated version. You have several queries, and then the attention becomes a function of I, depends on I. So you can write attentions of I, and we have this nice formula that it's the one that I discussed before. And if you have a dependence of the attention on I, you can call it also add of I. It's the same thing. Now, let me give you a snapshot of the full architecture of these transformers, and then we are gonna go into details, and we are gonna basically focus on some subparts of this architecture one by one, and at the end, I guarantee you, at the end of this video, you will have a complete view of this architecture. So we are gonna do step by step all of its parts. So this is a bit it. It's could seem long and complicated, but actually, in fact, it's not. It's rather simple if we analyze it step by step, and that's what we are gonna do. Well, we are gonna start from the beginning. Especially, we are gonna start from this part here, this bottom part here. So we start from the inputs, and we analyze this input embedding and positional embedding. So let's start from the beginning. As I said, we have our input, we do its embedding. So let's say that we have a sentence, we have the embedding vector v, but that could be a problem if we just do that, because the embedding vector v does not depend on the order of the words inside our sentence. So it doesn't see the permutations of the words inside the sentence. This could be a problem because imagine that you have these two sentences. So, ich bin schön. It is different in meaning, I mean. It is different from another sentence like schön bin ich. Why is it so? Because maybe since I put schön bin ich in front of this second sentence, maybe I should translate this second sentence in, for example, an English sentence that would sound like I am very handsome, because I am putting emphasis on the fact that I am schön or handsome. While the first one I would simply translate it I am handsome. So the position of the words inside the sentence is important. So a simple embedding does not see this, and that's a problem. So that's why the author of the paper proposed this positional embedding, which is a way to see and count the positions of the words inside the sentence and give different representations depending on the positions of the words. So two sentences with two different orders of words in their content, they will be translated, they will be embedded into two different vectors. That's the idea of this positional encoding that I won't go into details. I will just mention that those are defined with sinus and cosinus, depending on the label. If it's an even position number, or if it's a odd position number, you would use sinus or cosinus. But basically, the important thing to retain here is that this positional encoding sees the permutations of the words inside the sentence. And so the positional encoding of a sentence would be different depending on the position of the words. And so ich bin schön would have a different positional embedding with respect to schön bin ich. That's what we want here. So if we start from our sentence, we do the embedding part, the standard embedding part, and then we do our positional encoding part, where, again, we see the order of the words inside the sentence. So now we come back at the full view. So this is the full view of the transformers. We did this first part here. Okay, so now you know everything about input embedding and positional embedding. What I want you to notice now is that you can see this full architecture in two building blocks. You have a first block that is an encoder block, where the inputs are encoded, and then a second part, which you can think as the decoder, where the encoder is used as input. If you see, there is an arrow here that is fed inside the decoder, as well as the outputs. So the outputs means the words that are translated up to now. So we are starting our translation. We start from the first word. For the first word, we do all of this, and then the first word is fed as an input to produce the second word of the translated text, and so on and so forth. So we have two blocks, encoder, decoder, based on attention, and that is what transformers neural networks are. So let's start from the encoder now. So basically it's the same architecture again. I'm taking this green block here, and I am making basically a zoom on the encoder part. So we have described already this part, the input embedding, the positional embedding. Now notice that we have three arrows in this part, and they represent query, key, and value of the attention mechanism. And then we have also what is called a skip connection, in the sense that query, key, and values are used to compute this multi-head attention. But also there is a skip connection that I will describe later. So let's zoom a bit. So we have this embedding plus positional encoded vector. Let's say that there is this Q, K, and value part where the multi-head attention is computed. So I have to explain you now what is this multi-head attention. So it works like this. Let's say that, as I said, we have several words that we want to translate, several queries are possible. Then we have our keys, and then we have our values. So we have several queries, so we have several attentions, so we have heads. So that's what I mean here when I write this little schema here. So for each query, we have a certain attention. So for query 1, we have attention number 1, which is the sum of the similarities of all the values. Then we have query 2, this would give attention number 2, so imagine it's this one. Same thing, sum over all the values for the similarities, and so on and so forth. We have a certain number of heads. They are then all concatenated together into what it's called multi-head attention. So you can see here this layer concat and linear. Concat and linear means that basically all the heads that we have are concatenated one by one, and then there is this matrix W null that takes care basically of the shape. It changes the shape of this concatenated vector. So nothing complicated. So if we go back, so we are here, now you know what is this multi-head attention bit. Then there is this layer, which is add the norm layer. So we have this multi-head attention computed in the way that I just described. Then we have this skip connection. Skip connection means that this input here, this embedded vector, is also fed and kept as it is and add it to the output of the multi-head attention layer. Could seem a bit strange that we do this multi-head attention bit and also we do this skip connection, but at the end it is also natural, quite natural, in the sense that think about when you do the translation. Yes, you pay attention to the words. Let's say that you want to translate a certain word. You focus on some of the words, some particular words of the input original text, and that's the idea of this multi-head attention part. But still, you want to keep and have a look if you need. You want to read again the full text. So you want to preserve also the information about the full original text untouched. So that's why we have also this skip connection here that puts together this multi-head attention mechanism that I described, and still we keep track of the full original text untouched. So they are added together, the output of this multi-head attention bit plus the full embedded text, as I said. So add is simple, and then there is this normalization layer. Let me describe in few words what it is. Well, the idea is that if you have some random variable, you can always subtract its mean, its average value, and divide by its variance, so that you have another random variable, z, which has mean 0 and variance of 1. And this normally tends to help the gradient descent algorithm to have faster convergence. So also this normalization part is quite standard, nothing special about it, it just helps convergence. So we use it because it's good to use it. And now you should have a full understanding of this encoder block, where the last bit that I did not describe is a standard feed-forward neural network that uses as input the multi-head attention added to the positional encoded vectors. So it's a simple standard feed-forward neural network, and again here there is add the normalization layer, same thing that I described already. This thing is done nx times, when nx is small, a certain number of times. Imagine that, again, that you are making this translation, you want to read this text 2, 3, 4 times before you start your translations. So that's the idea also of nx. At the end, you put everything together, you have one output, let's say this, you are here. This would be the input for the decoder part. So you are happy with your encoder, you have done all of this. This goes inside the input for the decoder part that I'm going to describe. So for the decoder part, so this is the last bit. For the decoder part, so we have the input from the encoder, okay? So everything that I already described, everything gets summarized inside this nice input coming from the decoder. So you can imagine that this part here is the full decoder. This goes as an input inside the encoder, which has also other inputs. So we have the output shifted rights, it says. So basically you have the outputs that you produced up to now. So if you are translating, you have the first word that you translate. Then to produce the second word, you use the first word that you already translated, plus you use again this input coming from the encoder. You do the same thing on the output, so you have this output embedding plus the positional encoding. I described already what's the meaning of this positional encoding, and you need to do it normally and naturally also on the output words that you are translating. You know everything now about multi-head attention. Maybe I should mention also this masked multi-head attention. Basically, this is used to mask the future words, the one that you are not yet translated, because you don't want to see the future in a way. So you have to mask the words that you still haven't translated. Otherwise, you would spoil your training set. You would see the future, so the results of your training set wouldn't be reliable. So that's why you need this form of masked multi-head attention. It's basically the same thing as the standard multi-head attention that I described before, but you kill some words. So you put to zero the similarity, if you want, for the words that you cannot see because they are in the future. You haven't translated them yet, so they are masked. You cannot use them, so you kill them. So basically, the decoder part should be simpler now because we have described everything that we need inside the encoder part. So we have this output bit. This part is pretty similar to what we already described. We have the masked attention. Just as before, this becomes input to another multi-head attention layer that takes into account the input coming from the encoder plus the input coming from the masked head attention of the output. You have another bit of standard feed-forward neural network. Then you have a linear layer and a softmax layer where you output your next word. So what I call the translation number 1, I meant that the next word is, for example, hi or m or handsome or whatever. So you are outputting probabilities for different possible candidates for the next word inside your translation with a certain probability. That's what softmax does. So you have possibility of word with probability 0.6, then you have another candidate with probability 0.3 and another candidate with probability 0.1. This should complete your understanding of the architecture of the neural network. So everything should be clear now. Maybe let's come back. This is the full architecture. You should be able to understand every part of it. Now, you have all the ingredients. All in all, it's a rather simple architecture. I mean, it's complex, I admit that, but all in all, it's less complex than what we had before with recurrent neural nets, for example, or even worse with the LSTMs. So all in all, it's a rather relatively simple architecture that does its job well, and it's fast because it doesn't use recurrency, so it can be parallelized, and you can exploit GPUs to compute this, to compute the training, to perform the training of this architecture faster, way faster than recurrent neural networks that are actually dying because of this new architecture. So if you want, this architecture is a little bit a killer, and it's performing its job quite well. To conclude, let me give you a couple of examples of famous transformers. Well, there is this one which is called BERT, bidirectional encoder representation from transformers, and GPT. We have GPT-2, we have also GPT-3, and those architectures are successfully used to perform machine translations from one language to the next. That's why I was making lots of examples taken from machine translation, and also they are able to perform text generation. So if you give them a beginning of a story, they would write a story in a certain style based on the inputs, on the input text that you gave them. So they are performing quite well. They are a state-of-the-art technique for natural language process, and I invite you to have a look at the article that I cited at the very beginning of this presentation. I invite you to have a look at the article because it's well written, and it could give you insights of this nice architecture and this very interesting architecture. So I invite you to have a look at this Attention is All You Need paper. Very interesting one. Thank you very much for your attention. It's the case to say so. Until next time.